So in this video, I want to work through problem number 3 here, and it illustrates some of the reactions that we learned about in chapter 4 between acids and other reagents. Remember on the test, I'll give you the formula here, but what you want to do is to complete the reaction and then also balance the reaction. So sulfuric acid has that formula. Tells me it's a solution, so aqueous. And then zinc bicarbonate has this formula. Actually, there's going to be 2 of those. We'll also make that aqueous. And again, that information would be given to you on the test. And then your job is to figure out what the products are going to be. So one thing we learned about in chapter 4 is that if we have a carbonate salt with an acid, we generate water and CO2. And that reaction is specifically coming from the reaction between that carbonate portion of the ion here and then the protons associated with the acid. And then what's left over, then that is what's going to form our salt formula here. And zinc sulfate is going to be in a 1-to-1 ratio because zinc has +2 charge and sulfate has a -2 charge. So you just need a 1-to-1 ratio for the molecular formula. Now, if we look at the salt formula, the zinc and the sulfate are already balanced here. And so let's direct our attention to what's going on with the hydrogen and the bicarbonate or hydrogen carbonate ion. So, and let me just do that in green just to sort of talk about the chemistry that's going on here. And let me move it up above so I have plenty of room for the other problem. What does it mean for the H2 on sulfuric acid? Well, it means that we have 2 protons that are going to be given over to the carbonate, the hydrogen carbonate ion here. I actually have 2 of them in the formula. Notice what happens when I bring these together. Well, each one of these is going to form a carbonic acid molecule. Now, carbonic acid is basically unstable in solution, and it falls apart to form, well, that's where our water and our CO2 comes from. For every 1 molecule of the carbonic acid, we get 1 of each. Since we have 2 here, 2 and 2, and then that's going to balance out our reaction, and we're done. The other way to balance the equation, instead of going through what I wrote up here in green, you can just by inspection count up the hydrogens, carbons, and oxygens, and then you'll see you need 2 and 2 in front of the water and CO2 to balance out those elements. Another reaction that we learned about in chapter 4 is when metals react with acids. And there's a bunch of different combinations that you can do with this. Calcium is a fairly reactive metal. Hydrobromic acid is fairly reactive as well. And then what happens here is that we're going to generate hydrogen gas plus a salt. That salt is going to be coming from the metal and from the anion that's associated with the acid. And so that's going to be calcium bromide. Calcium is on the second family, so always has a +2 charge. Bromide is a halogen, always has a -1 charge. We need 2 bromides to balance out the +2 charge on the calcium. And that actually gives us our point of reference in terms of balancing out this reaction. If we put a 2 in front here to take care of the bromine, we'll notice that we've also taken care of the hydrogen. And the reaction is balanced. One thing I forgot to do is I also want to show the gas being formed there with the hydrogen. The other 2 types of reactions that we saw for chapter 4, well, one was actually a neutralization reaction, which let me just go ahead and write that out for this problem here. And then in a separate video, I'll actually then do the calculation. Okay, so when an acid and for us specifically now, it's a hydroxide salt. In this neutralization reaction, we get water and we get a salt being formed. And in this case, it's going to be aluminum sulfate. Aluminum always has +3 state. Sulfate always has a -3 state. And so what you can do is you can switch those numbers around to indicate what the values are going to be for the cations in the formula. And then to balance out this problem, if we approach this by just looking at the salt formula here, that can be very useful. For example, I need 2 aluminums, so 2 there. I need 3 sulfates, 3. And then what we see happening here, there's actually, well, there's 3 times 2, there's 6 protons. There's 3 times 2, 6 hydroxides. Right? Every time this reaction takes place, it forms water, and so 6 for the water molecule. The other type of reaction to be familiar with from chapter 4 is where, I won't do a full example here, but just something simple, something like HCl reacting with, I don't know, sodium sulfide. What happens here is, and this happens with any kind of sulfide, salt, but the hydrogen and the sulfide come together to form H2S, so hydrogen sulfide gas. So that's the 4th type of reaction to be familiar with from chapter 4. And then the other parts here, the sodium and then the chloride, are, well, they're essentially spectator ions, and they're the ones that form the other product. And then you'd go in and balance the equation here, which in this case, I guess I am doing an example. The 2 and 2 there should take care of it. I was looking at the sodium initially, and notice I need 2 sodiums here, so I need a 2 in front, and then that produces 2 chlorides, so I need a 2 in front here to balance out the chlorides. And then as it turns out, 2 hydrogens pairing up with the 1 sulfide produces our final product there, and it's balanced. Typical kind of balancing act for these metathesis reactions, when you have, or not even beyond just metathesis reactions, any of the reactions we see in chapter 4, within 2 or 3 steps, it should be balanced. If it's not, probably what's happened is that you've made an error in the molecular formula. Like you haven't brought the cation and the anion together in the proper ratio to get the correct molecular formula. That's usually the biggest error here. Okay, so I think that there's a pretty good set of examples for all the reactions in chapter 4. Okay, thanks.